In the quiet darkness of a clear night, far from city lights, you can look up and see a luminous band stretching across the sky. A river of starlight so dense and beautiful that ancient peoples told stories about it, imagining it as spilled milk, a celestial road, or the backbone of the night itself. This is the Milky Way, our home galaxy, seen from within. We live inside this vast spiral of stars, gas, and dust, orbiting slowly around a center we cannot see with our unaided eyes, a center hidden behind veils of interstellar clouds. For thousands of years, humans looked at this band of light and wondered what lay at its heart. We did not know we lived in a galaxy. That concept would come much later. We did not know that the fuzzy patches of light were distant star clusters and nebulae. And we certainly did not know that at the very center of our galaxy, hidden in the constellation Sagittarius, there lurked something extraordinary, a supermassive black hole 4,000,000 times the mass of our Sun, sitting silent and dark at the gravitational center of everything. This is the story of Sagittarius A asterisk, pronounced Sagittarius A star, the supermassive black hole at the heart of the Milky Way. It is a story told slowly, gently, like starlight traveling across the galaxy. It is a story of patient observation, of scientists peering through telescopes across decades, watching stars orbit an invisible point, measuring radio waves from the galactic center, and finally capturing an image of the shadow cast by the black hole itself. Close your eyes for a moment and imagine yourself floating in space, far above the disk of the Milky Way. Below you spreads a great spiral, like a cosmic whirlpool made of hundreds of billions of stars. Spiral arms sweep outward from a bright central bulge, traced by brilliant blue stars and glowing pink nebulae where new stars are being born. Between the arms lie darker regions, lanes of dust that obscure the light. And at the very center, where the stars crowd most densely, there's a point of absolute darkness, the black hole that holds everything together. Now imagine drifting closer, falling gently toward that center, passing through the outer spiral arms where our Sun resides, about 26,000 light-years from the galactic core. As you fall inward, the stars grow denser, the spaces between them shrinking. The light intensifies, and at the heart of it all, invisible but undeniable, Sagittarius A asterisk waits, not consuming everything around it, as you might expect, but sitting remarkably quiet, a sleeping giant that occasionally stirs when gas or dust wanders too close. This is a peaceful journey, a meditation on discovery and the nature of the universe. There is no danger here, no dramatic countdown, no crisis to resolve. There is only the slow, patient work of understanding, the accumulation of evidence over decades, the gradual revelation of one of the universe's most extraordinary objects. Let yourself relax into this story. Let the concepts wash over you like gentle waves. And together, we will explore the silent heart of the Milky Way. The galactic center lies in the direction of the constellation Sagittarius, approximately 26,000 light-years from Earth. This distance is almost incomprehensible to human minds. Light, traveling at 186,282 miles per second, takes 26,000 years to complete the journey from the galactic center to our eyes. When we observe the galactic center today, we see it as it was when our human ancestors were still living in small bands, hunting and gathering across prehistoric landscapes. But there's a fundamental problem with observing the galactic center. Between Earth and that distant region lie vast, dense clouds of interstellar dust. These clouds are not like the dust we find in our homes. They consist of microscopic particles of carbon, silicon, iron, and other elements, each grain smaller than a bacterium. These tiny particles are remarkably efficient at absorbing and scattering visible light. When we point optical telescopes toward the constellation Sagittarius, toward the brightest part of the Milky Way band, we see only the nearer stars and nebulae. The dust absorbs about 99.99% of visible light from the galactic center, effectively hiding it from our view. For centuries, this dust barrier made the galactic center inaccessible to astronomers. Early telescopic observers in the 17th and 18th centuries could see that the Milky Way appeared brightest and densest in the direction of Sagittarius, suggesting that the center of our stellar system lay in that direction. But they could not penetrate the obscuring dust to see what actually existed at that central point. The nature of the galactic center remained a mystery, hidden behind a cosmic veil. The breakthrough came with the development of radio astronomy in the 20th century. Radio waves have much longer wavelengths than visible light, thousands of times longer, and these longer wavelengths allow radio waves to pass through interstellar dust almost unimpeded. What blocks visible light becomes transparent to radio waves, like fog that blocks our vision but allows sound to pass through clearly. The story of radio astronomy's discovery of the galactic center begins in the 1930s with Karl Jansky, a young engineer working for Bell Telephone Laboratories in New Jersey. Jansky was assigned to investigate sources of static that interfered with radio communications. He built a large rotating antenna, mounted on wheels from a Model T Ford, that could turn to determine the direction from which radio signals were arriving. Over months of careful observations in 1932 and 1933, Jansky noticed a persistent source of radio static that appeared strongest when his antenna pointed toward the constellation Sagittarius. This radio emission rose and set with the stars rather than with the sun, proving it was coming from beyond our solar system. Jansky initially thought it might be coming from a nearby star, but further analysis showed the emission was too broad and diffuse. He concluded, correctly, that he was detecting radio waves from the center of our galaxy. This was a profound discovery, the first detection of radio emission from any astronomical object beyond the solar system. But its significance was not immediately appreciated. Jansky published his findings in 1933, but the discovery received little attention from the astronomical community. It would take decades before radio astronomy matured into a powerful tool for studying the universe. By the 1950s and 1960s, radio telescopes had improved dramatically. Engineers built larger antennas with more sensitive receivers, capable of detecting fainter signals and determining their positions more precisely. Astronomers began systematically mapping the radio emission from the galactic center region, and what they found was far more complex than anyone had anticipated. The galactic center, as revealed by these radio observations, is not a simple, peaceful place. It is a region of intense activity and energy, containing multiple distinct sources of radio emission. There are supernova remnants, the expanding shells of gas and magnetic fields left behind by exploded stars, glowing brightly in radio wavelengths. There are regions of hot, ionized gas heated to millions of degrees by radiation from massive young stars. There are mysterious, thread-like filaments of radio emission stretching for hundreds of light years across the galactic center, perpendicular to the galactic plane, whose origin remains debated even today. And at the very center of all this activity, radio astronomers detected a compact, bright source that would become known as Sagittarius A. This name, following astronomical convention, indicated that it was the brightest radio source in the constellation Sagittarius. But Sagittarius A turned out to be not a single object, but a complex of several distinct sources, each with its own characteristics and origin. The largest component of the Sagittarius A complex is Sagittarius A East, a shell-like structure about 25 light-years across. This is a supernova remnant, the debris from a massive star that exploded roughly 10,000 years ago. The expanding shell of gas creates a distinctive pattern in radio maps. Another component is Sagittarius A West, often called the mini-spiral a three-armed spiral structure of ionized gas orbiting within a few light-years of the galactic center. This gas is heated to about 10,000 degrees by ultraviolet radiation from nearby hot stars. But the most intriguing component of the Sagittarius A complex is Sagittarius A asterisk, the compact radio source at the absolute dynamical center of the Milky Way, the precise point around which all the stars, gas, and dust in our galaxy orbit. This object was first clearly detected and identified in February 1974 by astronomers Bruce Ballack and Robert Brown, who were using the Green Bank radio telescope in West Virginia to conduct high-resolution observations of the galactic center region. They discovered an extremely compact radio source, far smaller than anything else in the region, sitting exactly at the position that orbital dynamics predicted for the galaxy's central mass. The asterisk added to the name, making it Sagittarius A star, distinguished this compact source from the larger Sagittarius A complex and indicated its special nature. Even with the best radio telescopes, Sagittarius A asterisk appeared as a point source, unresolved, suggesting that the region emitting radio waves was extremely small by astronomical standards. Its position at the exact center of the galaxy was too precise to be coincidental. Its radio emission was remarkably steady over time, unlike the variable emission from pulsars or flaring stars. Everything about Sagittarius A asterisk suggested it was something extraordinary, something that might be the key to understanding what lay at the heart of our galaxy. Before we can truly appreciate what Sagittarius A asterisk is, we must understand the nature of black holes. Objects so strange, so extreme, that they challenge our intuitions about how the universe works. This understanding begins gently, with the familiar force of gravity, and builds gradually toward the extraordinary conditions that create black holes. Gravity is the universal attractive force between all objects with mass. It is gravity that holds you to Earth's surface, that keeps the moon orbiting Earth and Earth orbiting the sun, that binds stars into galaxies and galaxies into clusters. Isaac Newton, in the 17th century, gave us the first mathematical description of gravity. Every object attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. This simple law explained the orbits of planets with remarkable precision and allowed astronomers to predict eclipses, discover new planets, and understand the structure of the solar system. But Newton's law, while accurate for most purposes, is incomplete. It describes how gravity behaves, but not what gravity is. That deeper understanding came from Albert Einstein, who published his general theory of relativity in 1915. Einstein showed that gravity is not a force in the traditional sense, but rather a consequence of the curvature of space-time itself. Space-time is the four-dimensional fabric of the universe, combining 3 dimensions of space with 1 dimension of time. Einstein demonstrated that mass and energy curve this fabric, and objects move along the straightest possible paths, called geodesics, through the curved space-time. What we perceive as gravitational attraction is actually objects following these curved paths. The Earth orbits the Sun, not because the Sun pulls on it, but because the Sun's mass curves space-time, and Earth follows a geodesic path through that curved geometry. Einstein's equations describing this curvature are complex and difficult to solve. But within months of Einstein's publication, a German physicist named Karl Schwarzschild, while serving the German army during World War I, found an exact solution to Einstein's equations. Schwarzschild's solution described the curvature of space-time around a perfectly spherical, non-rotating mass. And buried within this solution was something remarkable and disturbing. Schwarzschild discovered that if you compress enough mass into a small enough region, the curvature of space-time becomes so extreme that something extraordinary happens. There forms a boundary, now called the event horizon, from within which nothing can escape. Not even light, the fastest thing in the universe. This radius, now called the Schwarzschild radius, depends only on the mass of the object. For an object with the Sun's mass, the Schwarzschild radius is about 3 kilometers. If you could somehow compress the entire Sun into a sphere only 3 kilometers across, it would become a black hole. The concept seemed almost absurd. How could gravity be so strong that even light cannot escape? Light travels at 300,000 kilometers per second. Nothing can move faster. Yet the mathematics was clear. If you create enough curvature in space-time, you create a region from which escape is impossible. This region came to be called a black hole, a term coined by physicist John Archibald Wheeler in 1967. For decades, black holes remained theoretical curiosities. Most physicists, including Einstein himself, doubted they could actually exist in nature. They seemed too extreme, too bizarre. But as our understanding of stellar evolution advanced through the mid-20th century, it became clear that black holes might not only be possible, but inevitable. Stars shine by converting hydrogen into helium through nuclear fusion in their cores. This fusion produces outward pressure that balances the inward pull of gravity, keeping stars stable. But eventually, stars exhaust their nuclear fuel. When a star runs out of fuel, the outward pressure disappears, and gravity causes the star to collapse. For stars with masses similar to our Sun, this collapse is relatively gentle. The outer layers drift away, forming a beautiful planetary nebula, while the core compresses into a white dwarf, a dense, hot sphere about the size of Earth, supported against further collapse by electron degeneracy pressure, a quantum mechanical effect. White dwarfs gradually cool over billions of years, slowly fading from view. But more massive stars meet more dramatic fates. When a star more than about 8 times the Sun's mass exhausts its fuel, it collapses rapidly and then explodes in a supernova, one of the most violent events in the universe. The outer layers are blown away at thousands of kilometers per second, while the core collapses into an incredibly dense object called neutron star. Neutron stars pack more than the Sun's mass into a sphere only about 20 kilometers across. They are so dense that a teaspoon of neutron star material would weigh billions of tons on Earth. Neutron stars are supported against further collapse by neutron degeneracy pressure, another quantum mechanical effect. But there is a limit to this support. If the collapsing core is more massive than about 3 solar masses, even neutron degeneracy pressure cannot prevent further collapse. The core continues to shrink, crushing matter beyond anything we can describe with known physics. According to general relativity, this collapse continues inexorably until all the mass is concentrated at a single point, a singularity surrounded by an event horizon. A stellar mass black hole is born. These stellar black holes, formed from individual massive stars, typically contain between 3 and a few dozen solar masses. But there exists another category of black holes, vastly more massive, supermassive black holes, containing millions or even billions of solar masses. These giants reside at the centers of most large galaxies, including our own Milky Way. Sagittarius A asterisk, with its 4 million solar masses, is one of these supermassive black holes. How supermassive black holes form remains one of astronomy's great puzzles. They might grow from stellar mass black holes that merge and consume surrounding matter over billions of years. Or they might form directly in the early universe from the collapse of enormous gas clouds. Or perhaps both processes contribute. What is clear is that most galaxies contain supermassive black holes at their centers, and these black holes play crucial roles in galaxy evolution. Black holes themselves emit no light. That is why they're called black holes. But matter falling toward a black hole does not simply disappear quietly. As matter spirals inward, it forms an accretion disk, and friction within this disk heats the material to millions of degrees. This superheated matter glows brilliantly across the electromagnetic spectrum before crossing the event horizon and vanishing forever. The accretion process makes black holes detectable despite their fundamental darkness, allowing astronomers to find and study them throughout the universe. The most compelling evidence that Sagittarius A* is a supermassive black hole came not from the black hole itself, which emits relatively little radiation, but from the stars orbiting around it. Beginning in the 1990s, two teams of astronomers embarked on ambitious observational programs to track individual stars in the galactic center with unprecedented precision. These observations, spanning more than 2 decades, would revolutionize our understanding of what lies at the heart of the Milky Way. The challenge was formidable. The galactic center is 26,000 light-years away, and even the orbits of stars close to Sagittarius A* span regions only a few light days across, incredibly tiny angles as seen from Earth. Additionally, Earth's turbulent atmosphere blurs astronomical images, limiting the resolution of ground-based telescopes. Observing individual stars near the galactic center requires the largest telescopes, the best cameras, and sophisticated techniques to overcome atmospheric blurring. 2 research teams took on this challenge. One team, led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Germany, used the European Southern Observatory's telescopes in Chile, particularly the Very Large Telescope. The other team, led by Andrea Ghez at the University of California, Los Angeles, used the Keck Observatory telescopes in Hawaii. Both teams employed infrared cameras, which can see through the dust that blocks visible light, and both used adaptive optic systems. Adaptive optics is a remarkable technology that corrects for atmospheric blurring in real time. The system uses a guide star, either a bright star in the field of view or an artificial star created by shining a laser into the upper atmosphere, to measure how the atmosphere is distorting the light. Then, a deformable mirror in the telescope rapidly changes its shape hundreds of times per second to compensate for the atmospheric distortion. This allows ground-based telescopes to achieve resolutions approaching the theoretical limit imposed by the telescope size, rivaling the sharpness of space telescopes. Beginning in the mid-1990s, both teams began taking images of the galactic center repeatedly, typically observing several times each year. Each image was carefully analyzed to determine the precise positions of individual stars. Over months and years, these stars moved perceptibly across the sky. By combining positions measured over many years, the teams could trace the paths of individual stars and determine their orbits. The stars were given designations S1, S2, S4, and so on in the European system, and S0-1, S0-2, etc. in the UCLA system. Some designations refer to the same stars observed by both teams. These stars are mostly hot, luminous blue stars, relatively young and massive, somehow residing in this chaotic environment near the supermassive black hole. One star in particular became famous, S2, also known as S0-2. This star is about 15 times the mass of the Sun and shines with the luminosity of thousands of suns. But what makes S2 extraordinary is its orbit. S2 follows a highly elliptical path around Sagittarius A*, with an orbital period of about 16 years. At its closest approach, called periapsis, S2 comes within about 17 light hours of Sagittarius A*, closer to the black hole than Neptune is to our Sun. At its farthest point, apoapsis, it recedes to about 1,400 light hours, a distance similar to that between our Sun and Saturn. The teams tracked S2 through multiple complete orbits. They watched it swing around the invisible point at the center, accelerating as it approached periapsis, reaching velocities up to 7,600 kilometers per second, about 2.5% the speed of light, then slowing as it receded toward apoapsis. The observations were precise enough to determine not just the orbit's size and period, but also its orientation in space, its eccentricity, and how these parameters changed over time. With these orbital parameters precisely measured, the astronomers could apply Kepler's laws of orbital motion, the same laws that govern the planets orbiting the Sun, to calculate the mass of the object that S2 orbits. Johannes Kepler, in the early 17th century, discovered that the square of a planet's orbital period is proportional to the cube of its average distance from the Sun. Newton later showed that this relationship depends on the Sun's mass. The same mathematics applies to any orbiting system. If you know an object's orbital period and size, you can calculate the mass of the central body. For S2, the calculation was straightforward but profound. The star orbits with a period of 16 years at an average distance of about 120 billion kilometers. Plugging these numbers into Kepler's equation yields a mass for the central object of approximately 4 million solar masses. And this enormous mass is concentrated in a region smaller than S2's closest approach, smaller than the orbit of Mercury around our Sun. No known astronomical object, except a black hole, could be so massive yet so compact. A cluster of 4 million stars packed into such a small volume would be dynamically unstable. The stars would collide and merge within a short time. A giant cloud of dark matter would not produce the radio and infrared emission observed from Sagittarius A star. Every alternative to a black hole fails to match the observations. The conclusion became inescapable. Sagittarius A asterisk is a supermassive black hole. But the story doesn't end there. The teams continued observing, tracking not just S2, but dozens of other stars in the galactic center. Each star's orbit provides an independent measurement of the central mass. Every orbit confirms the presence of approximately 4 million solar masses at the galactic center. The accumulated evidence, built up observation by observation over more than 20 years, is overwhelming. The observations also revealed relativistic effects, predictions of Einstein's general relativity that become noticeable in strong gravitational fields. As S2 approached periapsis in 2018, traveling at 2.5% light speed, just 17 light hours from a 4 million solar mass black hole, the gravitational field was strong enough that relativistic effects became measurable. The star's light was gravitationally redshifted. Its wavelength stretched slightly longer by climbing out of the black hole's gravitational well, exactly as predicted by general relativity. The orbit itself showed a subtle precession, a slow rotation of the orbital ellipse that differs slightly from Newtonian predictions. These measurements represent some of the most precise tests of general relativity in strong gravitational fields, and Einstein's century-old theory passed every test. The observations confirmed not just that Sagittarius A asterisk is a supermassive black hole, but that space-time around it behaves exactly as general relativity predicts. In 2020, Reinhard Genzel and Andrea Ghez were awarded the Nobel Prize in Physics for their decades of work tracking stars around Sagittarius A star. They shared the prize with Roger Penrose, the theoretical physicist who proved that black holes are inevitable consequences of general relativity. The Nobel Committee recognized not just the scientific discovery, but the extraordinary persistence, technical innovation, and collaborative effort required to track these stellar motions across more than 2 decades. It was a testament to the power of patient observation and the willingness to pursue answers across human timescales. One of the most surprising and important features of Sagittarius A asterisk is its remarkable quietness. Despite containing 4 million times the mass of our Sun, despite sitting at the gravitational center of a galaxy containing hundreds of billions of stars, Sagittarius A asterisk accretes very little matter and emits relatively weak radiation. Compared to supermassive black holes at the centers of other galaxies, which often blaze brilliantly as active galactic nuclei visible across billions of light years, Our galaxy's central black hole is extraordinarily subdued, a sleeping giant that only occasionally stirs. To understand why this matters, we must first understand what happens when black holes feed actively. As matter falls toward a black hole, it doesn't plunge straight in. Conservation of angular momentum, the tendency of orbiting objects to maintain their rotation, means that infalling matter spirals inward, forming a disk around the black hole called an accretion disk. Within this disk, friction between adjacent rings of orbiting matter converts orbital energy into heat, raising the temperature to millions or even billions of degrees. This superheated matter glows brilliantly across the electromagnetic spectrum, from radio waves through visible light to X-rays. For actively feeding black holes, the accretion disk can shine with the luminosity of trillions of suns, outshining the entire galaxy of stars surrounding it. These objects, called active galactic nuclei or quasars, were among the first supermassive black holes discovered precisely because they are so luminous. Astronomers detect them across vast cosmological distances, seeing them as they were billions of years ago when the universe was young and black holes fed more actively. The process doesn't stop with the accretion disk. Magnetic fields threading through the disk and surrounding the black hole can tap into the rotational energy of the black hole itself, launching jets of particles at velocities approaching the speed of light. These relativistic jets extend thousands or even millions of light years from the black hole, plowing through intergalactic space, creating vast lobes of radio emission, heating surrounding gas, and influencing galaxy evolution across enormous volumes. Sagittarius A displays none of this dramatic activity, at least not currently. Its radio emission is faint compared to active galactic nuclei. Its infrared and X-ray emission are weak. Observations suggest it accretes matter at a rate of perhaps 1,000th of a solar mass every 1,000 years, a trickle compared to what it could potentially consume. If Sagittarius A were feeding at the rate typical of active galactic nuclei, the inner Milky Way would be bathed in intense radiation that would sterilize planets and prevent life from developing across vast regions of our galaxy. Why is Sagittarius A so quiet? The answer lies in the nature of the gas surrounding it. Most of the gas in the galactic center is extremely hot, heated to temperatures of millions of degrees by shock waves from supernovae, by radiation from massive stars, and by other energetic processes. This hot gas is also moving rapidly with complex, turbulent motions. For gas to fall into the black hole, it must lose energy and angular momentum, settling into organized orbits that gradually spiral inward. But hot, turbulent gas resists this process. It carries too much thermal energy and too much angular momentum to fall inefficiently. Computer simulations of the galactic center environment show that most of the hot gas near Sagittarius A ends up being blown away rather than accreted. The gas follows chaotic, inefficient paths. Some of it gains energy and escapes. Some swirls around the black hole in turbulent eddies. Only a small fraction manages to lose enough energy and angular momentum to cross the event horizon. Despite its overall quietness, Sagittarius A is not completely dormant. X-ray and infrared observations detect occasional flares, brief increases in emission that last for a few hours, during which the luminosity increases by factors of 10 or more. These flares occur irregularly, perhaps once per day on average, though the rate varies. They likely represent individual events when clumps of gas or perhaps asteroids from disrupted systems fall close enough to the black hole to be heated and torn apart before crossing the event horizon. One dramatic flare was observed in September 2019, when infrared observations from the Keck Observatory showed Sagittarius * brightening to more than twice its normal infrared luminosity. The emission fluctuated rapidly over the 2-hour observation period. Such variations provide clues about the physical processes near the event horizon, where the strong gravity causes material to orbit in just minutes, creating rapidly changing patterns of emission. The low accretion rate and weak emission makes Sagittarius A** an unusual example of a supermassive black hole, but they're actually a blessing for us. An actively feeding black hole at our galaxy's center would create a harsh radiation environment throughout the inner galaxy. The intense X-rays and ultraviolet light would ionize gas in interstellar space, heat planetary atmospheres, and increase mutation rates in any life that might exist. The relatively dormant state of Sagittarius A* has likely been important for allowing life to develop in the Milky Way, including on Earth. Observations suggest Sagittarius A* was more active in the recent past, recent by astronomical standards, meaning within the last few million years. X-ray observations have revealed enormous structures called the Fermi bubbles, discovered by the Fermi Gamma-ray Space Telescope in 2010. These are gigantic lobes of hot gas extending about 25,000 light-years above and below the galactic disk, reaching halfway to the distance of our solar system from the galactic center. The bubbles are filled with high-energy particles and appear to have been inflated by powerful outflows from the galactic center. The Fermi bubbles likely formed during an episode when Sagittarius A* was feeding more actively, perhaps when a large gas cloud or cluster of stars fell into the galactic center. The energy released during this feeding episode drove winds of hot gas outward, perpendicular to the galactic disk, creating the bubbles. This activity ended perhaps a few million years ago, and the bubbles now represent a fossil record of that more active period. They slowly expand and fade, gradually mixing with surrounding gas, but they will remain visible for tens of millions of years. Radio observations provide additional evidence of past activity. There are structures in the galactic center called threads, long, thin filaments of radio emission oriented perpendicular to the galactic plane. These filaments may trace magnetic field lines that were shaped during periods of more active outflows from Sagittarius A star. Their current appearance suggests the black hole's activity varies over timescales of thousands to millions of years, alternating between relative dormancy and more active feeding episodes. Understanding why Sagittarius A* is currently so quiet helps astronomers understand the conditions required for active galactic nuclei. The difference between a quiet black hole like Sagittarius A* and a brilliant quasar seen in distant galaxies appears to be primarily the availability of cold gas that can efficiently fall inward. In the early universe, when galaxies were forming and merging more frequently, supermassive black holes had access to abundant cold gas, leading to the bright quasar era. As galaxies matured and gas was consumed or heated, black hole feeding became less efficient, and most supermassive black holes, including Sagittarius A*, settled into their current quiet states. This quietness, then, is not a permanent feature but a phase in the black hole's life. In the future, if large amounts of cold gas somehow reach the galactic center, perhaps during a merger with another galaxy, Sagittarius A* could awaken and feed actively again, dramatically changing the environment at the heart of the Milky Way. For decades after its discovery, Sagittarius A* remained invisible in the most direct sense. Its presence inferred from radio emission and from the orbits of surrounding stars, but never directly imaged. Astronomers dreamed of photographing the black hole itself, or more precisely, of imaging the shadow it casts against the glowing material surrounding it. This seemed almost impossibly difficult, but through international collaboration, technological innovation, and years of patient work, astronomers achieved this goal, producing the first image of Sagittarius A* in 2022. The fundamental challenge is one of resolution, the ability to distinguish fine details. At a distance of 26,000 light-years, even Sagittarius A *''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''' only about 12 million miles and about 12 million miles in diameter. This might sound large, but from Earth, it subtends an angle of only about 50 microarcseconds, roughly equivalent to seeing a donut on the surface of the moon. No single telescope on Earth, no matter how large, can achieve such resolution when observing at any practical wavelength. The solution is a technique called Very Long Baseline Interferometry, or VLBI. Instead of building one impossibly large telescope, astronomers use multiple telescopes spread across vast distances and combine their signals. The resolution of an interferometer depends not on the size of individual telescopes, but on the maximum distance, the baseline between them. To image Sagittarius A***, astronomers needed baselines of thousands of kilometers, which meant they needed a telescope effectively the size of Earth. This vision led to the Event Horizon Telescope Project, an international collaboration that brings together radio telescopes from around the world to create a virtual Earth-sized telescope. The participating telescopes include the Atacama Large Millimeter/Submillimeter Array, ALMA, in Chile, the Atacama Pathfinder Experiment, APEX, in Chile, the IREM 30-meter telescope in Spain, the James Clerk Maxwell Telescope in Hawaii, the Large Millimeter Telescope in Mexico, the Submillimeter Array in Hawaii, the Submillimeter Telescope in Arizona, and the South Pole Telescope in Antarctica. Together, these telescopes form a network spanning from Hawaii to Europe to the South Pole, creating baselines of up to 10,000 kilometers. The observations are conducted at a wavelength of 1.3 millimeters, which corresponds to a frequency of 230 gigahertz. This wavelength was chosen carefully. It's short enough to provide the necessary resolution, but long enough that Earth's atmosphere remains reasonably transparent. It's also a wavelength where the emission from material near the black hole is strong, making detection possible. VLBI observations require exquisite timing. Each telescope records the radio signals it receives, along with precise time stamps provided by atomic clocks synchronized to billionths of a second. The recorded data, many petabytes per observing campaign, is shipped on hard drives to central processing facilities because the data rate is too high to transmit over the internet. There, sophisticated software correlates the signals from different telescopes, searching for patterns that reveal the structure of the radio source. The Event Horizon Telescope first turned its attention to a different target, M87**, the supermassive black hole at the center of the giant elliptical galaxy Messier 87, located about 55 million light-years away. Though much more distant than Sagittarius A**, M87* is also much more massive, about 6.5 billion solar masses. Its event horizon, therefore, appears larger on the sky, making it a good target for the first attempt at imaging a black hole. In April 2019, the Event Horizon Telescope collaboration announced success, releasing the first image ever captured of a black hole. The image showed M87* as a bright ring of emission, glowing gas in the accretion disk and near the black hole, surrounding a dark central shadow. The shadow represents the black hole itself and the region just inside the photon sphere, where light can orbit the black hole. The diameter of the shadow, about 42 microarcseconds, matched predictions from general relativity for a black hole of M87**'''s mass. The image was both a triumph of observational astronomy and a stunning confirmation of Einstein's century-old theory. With M87* successfully imaged, the Event Horizon Telescope team turned to the more challenging target, Sagittarius A**. The challenge was not distance or size. Sagittarius A**'. S event horizon actually appears slightly larger than M87**, S as seen from Earth. The challenge was variability. M87* is so massive that material in its accretion disk orbits relatively slowly, completing an orbit in weeks or months. The emission pattern changes slowly enough that it remains essentially static during the hours of an observing session. Sagittarius A* is much smaller and less massive. Material in its accretion disk orbits in just minutes. The pattern of emission changes rapidly, swirling and evolving during the hours of observation. Imaging Sagittarius A* is like trying to photograph a restless child who won't hold still. You're trying to capture a clear image of something that's constantly moving. The Event Horizon Telescope observed Sagittarius A* in April 2017, the same campaign that observed M87*. But processing the data took much longer. The team had to develop new techniques to account for the variability, essentially averaging over many short snapshots and using sophisticated algorithms to reconstruct a stable image from the rapidly changing data. Finally, in May 2022, the Event Horizon Telescope collaboration announced their results and released the first image of Sagittarius A*. The image showed a glowing orange ring surrounding a dark central shadow, remarkably similar in appearance to the M87* image, despite the thousand-fold difference in mass. The ring has a diameter of about 52 microarcseconds, matching the predictions of general relativity for a 4-million solar mass black hole. The bright regions in the ring correspond to areas where emission is enhanced by relativistic effects. Light from gas moving toward us is amplified and blue-shifted, appearing brighter. The image confirmed what decades of other observations had suggested. Sagittarius A* is indeed a supermassive black hole, and the space-time around it behaves exactly as Einstein's equations predict. The shadow size, the ring structure, the brightness distribution all match theoretical models. The image also revealed that Sagittarius A* is likely spinning, though not at the maximum possible rate. The pattern of brightness in the ring provides clues about the black hole's spin and the orientation of its spin axis. Beyond its scientific significance, the image of Sagittarius A* captured imaginations worldwide. Here was direct visual evidence of one of nature's most exotic objects, something that had been purely theoretical less than a century ago. The image showed the heart of our galaxy, the anchor point around which our sun and billions of other stars orbit, rendered visible for the first time. The achievement represents the culmination of decades of work by hundreds of scientists, engineers, and support staff from institutions around the world. It required developing new technologies, building new telescopes, creating new data processing techniques, and coordinating complex international observations. The Event Horizon Telescope collaboration continues to work, improving their techniques, adding new telescopes to the network to increase resolution and sensitivity, and planning observations of other black holes throughout the universe. The region immediately surrounding Sagittarius A* is one of the most extreme environments in the observable universe. Here, gravity is so intense that it warps the fabric of space-time itself into curves and folds that challenge our everyday understanding of reality. Time slows down, light bends along curved paths, and the laws of physics manifest in their most dramatic forms. At the heart of this extreme region lies the event horizon, the boundary of no return. For Sagittarius A*, with its mass of 4 million suns, the event horizon has a radius of about 12 million kilometers, roughly 7.5 million miles, or about 17 times the sun's radius. This is the Schwarzschild radius, the distance from the singularity at which the escape velocity equals the speed of light. Once anything, matter, light, or information, crosses this boundary inward, it can never return. The future of anything inside the event horizon leads inexorably toward the central singularity. But the event horizon is not a physical surface or barrier. An astronaut falling towards Sagittarius A asterisk would detect nothing special upon crossing the event horizon. There is no wall, no membrane, no sudden change in conditions. The astronaut would simply pass through, continuing to fall inward, unaware that they had crossed the point of no return. Only later, when they tried to escape or send signals outward, would they discover that escape is impossible. Everything inside the event horizon, even light traveling at maximum speed, is pulled inexorably inward. From the perspective of a distant observer, however, the picture is very different. As an object approaches the event horizon, time dilation, the slowing of time in strong gravitational fields predicted by general relativity, becomes extreme. The closer to the event horizon, the slower time passes relative to distant observers. An observer watching something fall towards Sagittarius A asterisk would see it slow down dramatically as it approaches the event horizon. The infalling object's clock would appear to run slower and slower. Light from the object would be gravitationally redshifted, stretched to longer, redder wavelengths, as it climbs out of the deep gravitational well. In principle, the infalling object would appear to take infinite time to actually reach the event horizon, though in practice it would quickly become too dim and too redshifted to detect. This time dilation effect is not an illusion or observational artifact. Time genuinely passes at different rates in regions of different gravitational potential. Time near the event horizon of Sagittarius asterisk flows much more slowly than time here on Earth. Just outside the event horizon, at 1.5 times the Schwarzschild radius, lies another special region, the photon sphere. At this precise distance, photons, particles of light, can orbit the black hole in unstable circular paths. These orbits are unstable because any slight perturbation causes the photon to either spiral inward and be captured or spiral outward and escape to infinity. The photon sphere represents the innermost region where light can travel in closed loops around the black hole. For Sagittarius A asterisk, the photon sphere has a radius of about 18 million kilometers. This region plays a crucial role in creating the black hole shadow seen in the Event Horizon Telescope images. Light emitted by material just outside the photon sphere can orbit the black hole multiple times before escaping, creating intricate patterns of brightness and shadow. Light emitted inside the photon sphere cannot escape at all, contributing to the dark central shadow visible in the images. Farther out, at 3 times the Schwarzschild radius for a non-rotating black hole, lies the innermost stable circular orbit, the closest distance at which matter can orbit stably. Closer than this, orbits become unstable, and particles inevitably spiral inward. This distance, about 36 million kilometers for Sagittarius A asterisk, marks the inner edge of any accretion disk. Material orbiting closer is in its final moments before plunging across the event horizon. The intense gravity near Sagittarius A asterisk creates dramatic effects on light paths. Light does not travel in straight lines near massive objects, but follows curved paths through warped space-time. Close to the black hole, these curves become extreme. Light emitted from the accretion disk is bent along paths that can loop around the black hole, sometimes multiple times before escaping. This gravitational lensing creates complex patterns in observed images, with some regions of the accretion disk visible both as direct images and as secondary, tertiary, or higher-order images bent around the black hole. Another relativistic effect visible near Sagittarius A asterisk is Doppler boosting. Material in the accretion disk orbits at relativistic velocities, significant fractions of the speed of light. For a 4-million solar mass black hole, material at the innermost stable circular orbit orbits at about half the speed of light. Material moving toward an observer has its light blue shifted and amplified in brightness, while material moving away has its light red shifted and dimmed. This creates an asymmetry in the observed brightness of the accretion disk, with one side appearing brighter than the other. If Sagittarius A asterisk is rotating, and most black holes probably are, additional effects come into play. A rotating black hole drags spacetime around with it, a phenomenon called frame dragging or the lens-throwing effect. Near a rotating black hole, spacetime itself is forced to rotate in the same direction as the black hole's spin. This creates a region called the ergosphere, outside the event horizon, where nothing can remain stationary. Everything must rotate with the drag spacetime. The innermost stable circular orbit also depends on the black hole's spin. For a maximally rotating black hole, the innermost stable orbit can be as close as 0.5 times the Schwarzschild radius, compared to 3 times for a non-rotating black hole. This means rotating black holes can extract more energy from infalling matter, potentially making them more luminous. The structure of the ring in the Event Horizon Telescope images provides clues about Sagittarius A asterisk S spin, suggesting it is rotating but not at the maximum rate. These extreme conditions make the region near Sagittarius A asterisk a natural laboratory for testing general relativity in its strongest field regime. The theory has passed every test with remarkable precision, from the orbital precession of S2 to the gravitational redshift of light to the size and structure of the black hole shadow. Each measurement confirms Einstein's equations, now more than a century old, describing spacetime curvature with extraordinary accuracy. Yet there remain mysteries. At the very center of the black hole, general relativity predicts a singularity, a point where density becomes infinite and spacetime curvature becomes infinite. But infinity is a signal that our theory has broken down. At the smallest scales and highest energies, quantum effects must become important, and general relativity does not account for quantum mechanics. Understanding what actually exists at the center of a black hole will require a theory of quantum gravity, which remains one of physics' greatest unsolved challenges. For now, the event horizon shields this mystery from view. We cannot observe the singularity directly, and according to cosmic censorship conjectures and general relativity, singularities are always hidden behind event horizons, never naked and exposed to the outside universe. The interior of Sagittarius A asterisk remains inaccessible to our observations, a realm forever beyond our ability to explore directly. Though Sagittarius A asterisk currently feeds sparingly, consuming matter at a relatively slow rate, it has grown to 4 million solar masses over the galaxy's lifetime. Understanding how supermassive black holes feed and grow helps explain not only Sagittarius A asterisk S history, but also the connection between black holes and the galaxies that host them. A black hole grows by 2 main processes: accretion of gas and dust, and mergers with other black holes. Accretion is the primary growth mechanism for most supermassive black holes. As matter falls toward a black hole, it doesn't plunge directly inward but spirals gradually, forming an accretion disk. The physics of these accretion disks is complex and fascinating. In an accretion disk, matter orbits the black hole, with inner regions orbiting faster than outer regions, according to Kepler's laws. This differential rotation creates friction between adjacent rings of material. Friction converts orbital kinetic energy into heat, raising the temperature of the disk. The hottest regions emit high-energy radiation, ultraviolet light, and X-rays, while cooler outer regions emit optical and infrared light. For actively accreting black holes, the luminosity from the accretion disk can be enormous, sometimes outshining the entire host galaxy. The efficiency of converting mass into energy through accretion is actually higher than nuclear fusion. While fusion converts less than 1% of mass into energy, accretion onto a black hole can convert up to about 10% of the infalling mass into radiated energy, depending on the black hole's spin and the details of the accretion process. But not all matter that enters an accretion disk ultimately falls into the black hole. Outflows and winds can drive material away, returning it to the surrounding environment. The processes governing accretion are complex and involve magnetic fields, turbulence, radiation pressure, and other effects that are still not fully understood. Magnetic fields play a crucial role. Gas in accretion disks is ionized. Atoms are stripped of electrons, making it an electrically conducting plasma. This plasma carries magnetic fields with it as it moves. The magnetic fields can become twisted and amplified by the disk's rotation, generating magnetic turbulence that enhances friction and accretion. They can also launch outflows and jets of material that escape from near the black hole at nearly the speed of light. Around more active supermassive black holes than Sagittarius A *, these jets are spectacular phenomena. They consist of particles accelerated to relativistic speeds along magnetic field lines that thread the inner accretion disk and surround the black hole. The jets extend for thousands or millions of light years, far beyond their host galaxies, and can emit intensely across the electromagnetic spectrum. Some jets contain enough energy to significantly affect the evolution of galaxy clusters, heating intergalactic gas and preventing it from cooling and forming stars. Sagittarius A * does not currently produce such dramatic jets, though it may have in the past. The Fermi bubbles mentioned earlier likely formed during a period of more active outflows, perhaps a jet-like structure oriented perpendicular to the galactic disk that inflated these enormous lobes of hot gas. Computer simulations of gas dynamics near Sagittarius A * reveal why its current accretion rate is so low. The gas in the galactic center is extremely hot, millions of degrees, and highly turbulent. Hot gas has high pressure and resists compression, making it difficult for gravity to pull it inward. Much of the gas near Sagittarius A * flows in chaotic patterns, swirling around the black hole in complex motions but never settling into an organized accretion disk. Additionally, the gas carries angular momentum. It's rotating around the galactic center. For the gas to fall into the black hole, it must lose angular momentum. This typically happens through interactions with magnetic fields or through gravitational torques from asymmetries in the gas distribution. But these processes are inefficient in the current galactic center environment, resulting in the low accretion rate we observe. Occasionally, larger amounts of matter do reach Sagittarius A*. When a molecular cloud wanders too close, tidal forces from the black hole's gravity can tear it apart, sending some material into the black hole. When a star passes too close, within a distance called the tidal disruption radius, it too can be torn apart, its gas forming a temporary accretion disk that feeds the black hole over weeks or months, creating a bright flare visible across the galaxy. Such tidal disruption events are rare around Sagittarius A*, estimated to occur perhaps once every 10,000 to 100,000 years. But they may account for some of the evidence of past activity, including the Fermi bubbles. A star wandering too close and being torn apart could provide enough fuel for a temporary period of enhanced activity. The second way black holes grow is through mergers. When two galaxies collide and merge, their central supermassive black holes eventually spiral together and coalesce into a single, larger black hole. This process releases tremendous energy in the form of gravitational waves, ripples in space-time itself, predicted by general relativity and first detected directly in 2015 by the LIGO and Virgo observatories. Sagittarius A* will undergo such a merger in the distant future. The Andromeda Galaxy is approaching the Milky Way at about 110 kilometers per second. In approximately 4.5 billion years, the two galaxies will collide. The collision will not be catastrophic for individual stars. Space is so vast that actual stellar collisions will be rare, but it will dramatically reshape both galaxies. The collision will trigger bursts of star formation as gas clouds collide and compress. And eventually, perhaps 1 billion years after the initial collision, Sagittarius A* and Andromeda's central black hole will merge. Andromeda's central black hole is more massive than Sagittarius A*, containing about 100 million solar masses. When they merge, the final black hole will contain roughly 104 million solar masses. The merger will emit gravitational waves detectable across the universe, carrying away about 5% of the combined mass as pure energy, radiated in the form of space-time ripples. This merger lies billions of years in our future, but it illustrates that Sagittarius A* is not static. It has grown over billions of years and will continue growing, albeit slowly, until the distant future when it merges with other supermassive black holes. Each phase of growth has shaped not just the black hole itself, but the entire galaxy surrounding it, influencing star formation, gas distribution, and the overall evolution of the Milky Way. Supermassive black holes, like Sagittarius A*, are not passive residents at the centers of galaxies. They actively influence galaxy evolution through a complex feedback process, where the energy released during black hole feeding affects the surrounding galaxy, which in turn determines how much fuel reaches the black hole. This interplay between supermassive black holes and their host galaxies is one of the most important discoveries in modern astrophysics. The connection was first noticed through correlations. In 2000, astronomers discovered that the masses of supermassive black holes correlate remarkably tightly with properties of their host galaxies, particularly with the velocity dispersion of stars in the galactic bulge, the measure of how fast stars are moving in random directions in the central region of the galaxy. Galaxies with faster-moving stars in their centers harbor more massive, supermassive black holes. This correlation, known as the M-sigma relation, M for black hole mass, sigma for velocity dispersion, was unexpected and profound. Why should black holes, which are tiny compared to galaxies, Sagittarius A*, its event horizon is billions of times smaller than the Milky Way, correlate so tightly with galaxy-scale properties? The correlation suggests that black holes and galaxies grow together, their evolution intimately linked. The Milky Way fits this relationship precisely. With Sagittarius A*, S mass of 4 million solar masses and a bulge velocity dispersion of about 110 kilometers per second, our galaxy sits exactly on the M-sigma relation established by studying hundreds of other galaxies. This suggests that whatever processes created this correlation operate universally across galaxies of different types and masses. The mechanism connecting black holes and galaxies involves feedback, energy released by the black hole affecting its environment. When a supermassive black hole feeds actively, the energy released can heat surrounding gas to millions of degrees, driving powerful winds that blow gas out of the galaxy or prevent it from cooling and falling inward. This energy injection can regulate star formation by removing the cold gas needed to form stars, or by heating gas so it cannot collapse under gravity. Computer simulations of galaxy formation show that without black hole feedback, theoretical models produce galaxies that are too massive and contain too many stars compared to observed galaxies, including black hole feedback in the simulations, modeling how energy from accreting black holes heats and expels gas, produces galaxies that match observations much better. This suggests that supermassive black holes play a crucial regulatory role, preventing galaxies from converting all their gas into stars. The feedback process has several phases. During the bright quasar phase, when the black hole feeds rapidly, intense radiation from the accretion disk heats surrounding gas and drives powerful winds. These winds can reach velocities of thousands of kilometers per second, carrying away gas that would otherwise form stars. The winds can extend throughout the galaxy and beyond, affecting the intergalactic medium. Later, when the black hole's fuel supply diminishes and accretion slows, jets become more important. Many supermassive black holes produce jets even when not in the bright quasar phase. These jets, powered by magnetic fields and the black hole's rotation, can inflate enormous bubbles in the hot gas surrounding galaxies, preventing the gas from cooling and falling inward. Observations of galaxy clusters show many examples of these bubbles, cavities in the hot X-emitting gas carved out by jets from central black holes. Sagittarius A likely went through phases of more active feedback in the past. The Fermi bubbles represent evidence of past energy injection, when outflows from the galactic center swept up gas and inflated these enormous structures. While less dramatic than the feedback from the most active supermassive black holes, this energy injection would have affected star formation in the central regions of the galaxy and influenced the distribution of gas. The regulation works both ways. Black hole feedback affects the galaxy, but the galaxy also determines the black hole's growth. The amount of gas available to fuel the black hole, the rate at which gas can lose angular momentum and fall inward, and the dynamics of the galactic center all depend on galaxy-scale processes. Mergers between galaxies can funnel large amounts of gas toward the center, triggering periods of rapid black hole growth. Conversely, in isolated galaxies that have consumed most of their gas, black holes starve, entering the quiet phase we observe for Sagittarius A star. This coevolution helps explain why supermassive black holes exist at the centers of most large galaxies. They didn't just happen to end up there. They formed and grew together with their host galaxies through a shared history of star formation, gas accretion, mergers, and feedback. The black hole and the galaxy are partners in a cosmic dance, each influencing the other's evolution. Understanding this coevolution remains an active area of research. How do the first supermassive black holes form in the early universe? How does feedback operate in different types of galaxies? How precisely do black holes regulate star formation? These questions drive ongoing observations with telescopes like the James Webb Space Telescope, which can observe the earliest galaxies and quasars, and with X-ray observatories that can study feedback in action. Sagittarius A* provides a crucial laboratory for studying these processes. Being so close in astronomical terms, we can observe it in unprecedented detail, studying phenomena that occur on scales of light hours near the event horizon, tracking individual stars on decade timescales, and seeing how the black hole interacts with its immediate environment. Lessons learned from Sagittarius A* inform our understanding of supermassive black holes throughout the universe. Looking into the future of Sagittarius A* means contemplating timescales that dwarf human history, that stretch across billions and even trillions of years. The black hole's future evolution is tied to the fate of the Milky Way itself and ultimately to the long-term evolution of the universe. In the near term, by which astronomers mean the next few million years, Sagittarius A* will continue much as it is now. It will occasionally consume clumps of gas or stellar material that wander too close, producing flares that briefly increase its luminosity. It will continue accreting matter at its current modest rate, gradually adding to its mass. Over 1 million years at current accretion rates, Sagittarius A* might gain a few hundred solar masses, a tiny fraction of its total mass, but growth nonetheless. There exists a possibility, though we cannot predict when, of a larger feeding event. If a molecular cloud's orbit brings it close enough to Sagittarius A*, tidal forces could tear the cloud apart, funneling some of its gas into the black hole. Such an event could increase Sagittarius A*'s luminosity dramatically for weeks, months, or even years, making the galactic center much brighter in X-rays and possibly other wavelengths. Ancient records from Earth might preserve observations of such events. Unexplained brightening of the Milky Way center, though none have been definitively identified. On longer timescales, hundreds of millions to billions of years, Sagittarius A**'s fate is tied to the Milky Way's interactions with other galaxies. The most significant event in the Milky Way's future is the collision with the Andromeda Galaxy. This collision is not a distant speculation, but an inevitability, confirmed by decades of observations measuring Andromeda's motion through space. Andromeda is approaching at about 110 kilometers per second. The collision will begin in roughly 4.5 billion years, a timescale comparable to the age of Earth and the Sun. When the two galaxies collide, the interaction will unfold over hundreds of millions of years. First, the galaxies will pass through each other, their shapes distorted by mutual gravitational attraction. Stars themselves will rarely collide. The distances between stars are so vast that even when galaxies merge, direct stellar collisions are improbable. But the galaxy's overall structures will be dramatically disrupted, with tidal forces pulling streams of stars into long tails and bridges. Gas clouds will collide and compress, triggering intense bursts of star formation. Starburst episodes that will briefly make the merging system far more luminous than either galaxy was individually. The sky, as seen from planets around surviving stars, will become a spectacular display of newly formed massive stars, glowing nebulae, and the intermingling structures of two great spirals becoming one. As the merger proceeds, the two galactic centers, each containing a supermassive black hole, will spiral toward each other. Sagittarius A**, with its 4 million solar masses, and Andromeda's black hole, with roughly 100 million solar masses, will gradually close the distance between them, drawn together by dynamical friction, the process by which a massive object moving through a sea of stars and gas loses energy and momentum through gravitational interactions. Eventually, perhaps a billion years after the initial collision, the two black holes will form a binary system, orbiting each other at ever-decreasing distances. As they orbit, they will emit gravitational waves, ripples in space-time that carry away energy and angular momentum. This energy loss causes the orbit to shrink, bringing the black holes closer together in a process that accelerates as the separation decreases. In the final moments before merger, the two black holes will orbit each other many times per second, emitting powerful gravitational waves detectable across the universe. Then they will coalesce, their event horizons merging into a single horizon surrounding a final black hole of about 104 million solar masses. The merger will release about 5% of the combined mass as energy in gravitational waves, equivalent to the energy of several solar masses completely converted to radiation, making it one of the most energetic events in the universe. The final black hole will likely be spinning rapidly, its rotation induced by the orbital angular momentum of the merging black holes. It will settle into its new equilibrium over a timescale of hours or days, emitting additional gravitational waves as perturbations in its event horizon ring down like a struck bell. This merged black hole will sit at the center of the new galaxy formed from the Milky Way and Andromeda, often called Milkomeda in speculative literature. This galaxy will likely be an elliptical galaxy, a more spherical, less structured system than the current spirals, containing the stars from both progenitor galaxies. Looking even farther forward into the truly distant future billions of years hence, Sagittarius A**'s descendants will continue to exist even as the universe changes dramatically around them. The universe is expanding, and the expansion appears to be accelerating, driven by dark energy. This acceleration will eventually isolate groups of gravitationally bound galaxies from each other, stretching the space between them until they can no longer interact. Star formation will continue for tens of billions of years, but gradually the raw material, hydrogen and helium gas, will be consumed. Stars will continue to be born, live, and die, but at ever-decreasing rates. Eventually, perhaps 100 trillion years from now, the last star will form. After that, no new stars will be born, and the existing stars will gradually burn out. The smallest, coolest stars, red dwarfs, can burn for trillions of years, far longer than the current age of the universe. But eventually, even these will exhaust their fuel and fade to cold, dark stellar remnants. The universe will enter what cosmologists call the degenerate era, where the primary objects are white dwarfs, neutron stars, and black holes, with any remaining planets, asteroids, and other debris slowly orbiting through an ever-darkening cosmos. Black holes will persist through all of this. They don't burn fuel or radiate significantly through normal processes, but they're not completely eternal. Stephen Hawking showed in 1974 that black holes emit faint thermal radiation, now called Hawking radiation, due to quantum effects near the event horizon. This radiation is incredibly weak for large black holes, but it means black holes very slowly evaporate, losing mass over time. For a black hole the mass of Sagittarius A *S future descendant, perhaps 100 million solar masses, the evaporation time is about 10 to the power of 100 years. This is a number so large it defies comprehension. A googol years, far longer than the current age of the universe. But given infinite time, even this will pass, and eventually the black hole will evaporate completely, its mass converted to radiation, leaving behind only the fading glow of Hawking radiation in an empty universe. But these timescales are so vast, so far beyond anything we can truly grasp, that they exist more as mathematical possibilities than as futures we can meaningfully contemplate. For all practical purposes, Sagittarius A* and its descendants are eternal, persisting as long as the universe permits complex structures to exist. We have journeyed together from the observable sky above Earth, through radio waves and infrared light-penetrating dust, to the very center of our galaxy, where Sagittarius A* resides. We have explored the patient decades of observation that revealed its presence, the theoretical framework that explains its nature, and the remarkable achievement of imaging its shadow. Now, as we conclude this journey, we return to contemplate what this black hole means for our understanding of the universe, for the story of human discovery, and for our place in the cosmos. Sagittarius A* sits at the gravitational center of the Milky Way, anchoring our galaxy with its 4 million solar masses. It is not the violent monster of popular imagination, voraciously consuming everything nearby, but rather a quiet giant, accreting matter slowly, disturbing its surroundings minimally, allowing the galaxy to flourish around it. Its gravity provides stability, organizing the orbits of billions of stars, maintaining the structure of the galactic center. Yet despite its relative quietness, Sagittarius A* remains one of the most extreme objects in nature. Its event horizon marks a boundary beyond which our understanding breaks down, where even light cannot escape, where time itself flows at a different rate than in the regions far from its influence. Near the black hole, space-time is warped into curves so extreme that the familiar rules of geometry no longer apply, where the shortest path between 2 points is not a straight line, but a curve bent by gravity. The discovery of Sagittarius A* represents a triumph of human curiosity, patience, and ingenuity. For decades, astronomers tracked stars year after year, accumulating observations that would eventually reveal the invisible mass they orbited. Engineers developed adaptive optics systems that could correct for Earth's turbulent atmosphere, achieving resolutions that rivaled space-based observations. Theorists refined their understanding of general relativity, making predictions that could be tested against increasingly precise measurements. And ultimately, the Event Horizon Telescope collaboration brought together telescopes from around the world to create an Earth-sized instrument capable of imaging the black hole shadow. This achievement required not just technological advancement, but also institutional commitment. Funding agencies willing to support decades-long observational programs, universities and research institutes fostering collaboration across borders and disciplines, and a scientific community maintaining focus on fundamental questions even when answers seemed impossibly distant. The Nobel Prize awarded to Reinhard Genzel and Andrea Ghez in 2020 recognized not just individual brilliance, but the sustained collective effort that makes such discoveries possible. The story of Sagittarius A also reminds us of how much remains unknown. We have determined the black hole's mass and location with precision. We have imaged its shadow and measured how space-time curves around it. But profound mysteries remain. What actually exists at the center, at the singularity where our theories predict infinite density? How do supermassive black holes form in the early universe? How exactly do they influence galaxy evolution through feedback? Why does Sagittarius A accrete so little while other supermassive black holes feed ravenously? Each answer we find opens new questions. The Event Horizon Telescope's images of Sagittarius A and M87 have confirmed general relativity's predictions with remarkable precision, but they've also revealed new puzzles about magnetic fields, turbulence, and accretion processes near event horizons. Future observations with improved instruments will undoubtedly reveal additional complexities, refining our understanding while also exposing new gaps in our knowledge. There is something profound about humanity's relationship with these distant objects. We will never visit Sagittarius A star. Even traveling at the speed of light, the journey would take 26,000 years. The black hole will never directly affect our daily lives. Yet we devote enormous effort to understanding it, building telescopes, developing theories, analyzing data, all to comprehend something we can never touch, never approach, never experience except through instruments and mathematics. This effort speaks to something essential about human nature: our drive to understand, our refusal to accept ignorance about our surroundings, our need to know what lies beyond the next horizon, even when that horizon is 26,000 light-years away and hidden behind veils of dust. We explore not for practical benefit, but because the exploration itself is meaningful, because understanding our place in the universe enriches our existence in ways both tangible and ineffable. Sagittarius A also connects us to deep time. The light we observe from the galactic center was emitted 26,000 years ago, when human civilization was just beginning, when our ancestors were painting animals on cave walls and learning to shape stone tools. The black hole we observe today, as it was then, continues to exist in the present, now 26,000 years older, having accreted a bit more mass, having influenced the orbits of countless stars that pass nearby. When we observe Sagittarius A*, we are touching a piece of the past, seeing across both space and time. And looking forward, we know that Sagittarius A* will persist long after human civilization has ended, long after Earth itself has been transformed beyond recognition by the Sun's evolution into a red giant billions of years hence. The black hole will witness the collision of the Milky Way with Andromeda, will merge with Andromeda's central black hole, will sit at the center of the resulting galaxy through eras we can barely contemplate. In a real sense, Sagittarius A* is more permanent than anything in our everyday experience, more enduring than mountains or oceans or even stars. As you drift towards sleep, let your mind rest on this image. Deep in the heart of the Milky Way, hidden behind dust, but revealed through patient observation, sits a darkness that is also a presence, a mass so great it warps space-time, a gravity so intense it anchors our galaxy, a mystery so profound it challenges our understanding of reality itself. Around this darkness, stars orbit in their ancient dance, some completing circuits in mere decades, others in thousands or millions of years. Gas glows faintly in the black hole's vicinity, heated by friction and magnetic fields, occasionally flaring brighter when matter falls closer to the event horizon. And surrounding everything, the Milky Way's hundreds of billions of stars continue their own orbits, all bound by the shared gravity of dark matter, stars, gas, and a supermassive black hole at the center. The universe contains many wonders: distant galaxies, exploding stars, colliding neutron stars, exoplanets that might harbor life. But few are as fundamentally mysterious, as emblematic of nature's extremes, as the supermassive black holes at galactic centers. They represent the endpoints of gravity's influence, the places where matter and energy compress so far that space-time itself breaks, where our physics encounters its limits, where we glimpse the boundaries of the knowable. And yet we do not simply accept this mystery. We probe it, measure it, image it, seeking to understand even what seems beyond understanding. This is the human endeavor at its finest: curiosity meeting patience, technology enabling insight, collaboration achieving what individuals cannot. Sleep now, knowing that the galaxy's heart beats silently, invisibly, but measurably. That darkness at the center is not an absence, but a presence, not an ending, but a beginning of understanding. The silent heart of the Milky Way remains, patient and vast, waiting to reveal more secrets to those who take the time to listen, to watch, to wonder.